We'll now look at some more interesting examples of metrics. So the HouseDown distance is a metric on sets within a metric space. Okay, so suppose let's now fix a metric space. Let's fix a metric space. We get a distance between sets which doesn't give a metric in full generality, but enough to be very interesting and important. So here we have the HouseDown distance. But first, before we talk about the distance between two sets, roughly these two sets are supposed to be close to each other. This is a typical example because their points are all close. Okay, but on the other hand, a smaller set is not close to the bigger set because there are points from this that are far away from the other one. So this is what we want to capture. But before we do that, we should first talk about small and big sets. How big is a set? So for that, well, the size could be infinite of a set. So let's define definition. So let's say A in X is bounded if the set, let me write the set dxy where x and y in A. So this is a subset contained in R is bounded above, which can be spelt out as there exists M such that so and so happens. Okay, and definition, if we have a bounded set, if A is bounded and if it's not allowing values infinity, define diameter of A as the supremum of the distance between points. Okay. So this is our first step, which is the distance between the size of a set. This was just a definition, it didn't tell us much. But if a diameter is 0, then it's a single point that you can see. So remark, probably the only proposition we can have about this, diameter of A equals 0 if and only if A, well, I suppose strictly speaking is empty or A is a single point. Whether the first case comes or not depends on your conventions. Okay, so this was our first step, but now what we want to do is next, we want to define the distance from a set. Now this will have non-trivial properties, so we'll define it and then we'll look at it. So suppose A is a set. So A is contained in X is a set, and suppose X is any point. We define the distance between A and X as the distance to the nearest point. But as usual, there may not be a nearest point. So we will look at the infimum of X is a bad terminology because X is taken. Let's say infimum over A in A, or cleanest we'll write it as the infimum of a set. Infimum of the distance between X and A, where A is a point in A. Okay, so looking at this distance and between A and X is infimum of distance of X and A. Here's something to prove, but let's look at an example before we prove anything. Okay, so like for example, suppose I take X is R, and of course just to clarify, distance between x, y is mod x minus y, the only distance we have considered. We'll take A to be the rational numbers and take X to be pi. Then we know that distance between A and X is 0. I mean, we can see this because this is the infimum of mod of x minus pi, and or for consistency of notation I should say A minus pi, where A is in rational numbers. And pi can be arbitrarily well approximated by rational numbers. So if I have a set and I have a point, well, we would like to say that the point is a positive distance away unless it's actually in the set, but that's not true. For rational numbers, that's not true. But we do have a theorem here, not a hard one. Okay, that is, if A is closed, then for all x in A, we have distance between AX is 0 if and only if, I'm sorry, that's not x in A, for which this condition is silly, but for all x in X, if and only if little x actually is in A. Well, the 1/2 is true for any set. If you have a point in a set, of course the distance is 0, because in the infimum we'll include a 0, which is the point in itself. But if you have a closed set, then we have a point which is of a positive distance. Indeed, the converse is also true, but we won't prove it now because we don't need it right now. We'll leave it as an exercise. Okay, so if A is closed, then the distance is positive. Okay, so let's see what is the point here. Well, if it's closed, we know the complement is open. Okay, so if A is closed, well, first of all, okay, let's dispose of the other case later. If A is closed, x minus A is open. So by definition of a topology given by basis, hence for all x in X, if x is not in A, I want to show the distance is positive, there exists r greater than 0 such that we have a ball like that. Ball around x of r is contained in x minus A. What does this mean? That is, for all, let's say, y in X, if y is in this ball, distance between y and x is less than r, implies y belongs to x minus A, that is, y does not belong to A. And so the contrapositive of this is just saying that if I take this infimum, therefore infimum of, I call this point little x here, yeah, which it is. So therefore, so I'm write the definition of the set. So anything y does not belong to A. So the contrapositive says that A belongs to A implies that the distance between A and X is greater than R for all A. Therefore, the infimum of this distance mod it's not mod always, but distance between X and A with A in A is greater than or equal to R, which is positive. So the distance of a point not in the set is positive from the set. Okay. So for the converse, really, well, one could do it by hand here, but it would make more sense. It would be more intuitive once we have more definitions of closures and interior points and so on. So we'll revisit that at some point or leave it as an exercise at some appropriate point. Okay, we know the distance between a point and a set. So right now we'll just define the HouseDown distance and then leave it to the next video to prove that it's a distance. We want a distance between two sets, but if those sets are infinite, then we have a problem. Okay, so let's assume let A1, A2 be bounded sets. We want a distance that is symmetric, okay, and neither the minimum nor the maximum distance work well, because the minimum distance is bad, since if I took two sets like this, they are very close to each other, and our third set here can be close to this one, but this set and this set are not close to each other. So triangle inequality is violated. Anyway, it's not in the spirit. On the other hand, if I took maximum distance, well, of a set itself would be the diameter. And if you even rule out that case as a special case, if you slightly perturb the set, you'll have a problem, or you'll violate triangle inequality with a set in itself. Okay, so all these things mean that we cannot define it this way, but HouseDown had the clever idea of saying we'll write it in a different way. We find the smallest r, or infemal r, so that if I take an r neighborhood of one set, it engulfs the other set, and vice versa. If I take an r neighborhood of this set, it engulfs this set. Okay. So we could define it that way, but we'll define it equivalently in terms of distance between points and sets. So we'll define HouseDown distance between A1 and A2 as the maximum of two quantities, and let's see what they are. So the first one is we take, given a point here, we know its distance to the other set, namely we take the nearest point. This was not true picture. If I have a point here, the nearest point is probably this one. I take the nearest point on this set, and so I'm looking at the distance of this point from this set, but I maximize over this set. So we are saying that this is what you have to do to take the neighborhood, to make sure that every point is in an R neighborhood of this. So we maximize two quantities. First of all, we maximize, but since it's an infinite set, supremize the distance between A1 and little a2, where a2 is in a2. This is one term. So for the first set, so if a1 and a2 are two sets, for each point in a2 we are looking at how far it is from a1 and maximizing over a2, but we have to flip and do the other way also. So it's a maximum of two terms. This is split across two lines. Distance between a2 and little a1, and this time little a1 is in a1. Okay, so this is what is called a Hausdorff distance. I have to close the brace to. It's the maximum of these two values. So now in this generality, this is not a distance. Okay, so for example, if I looked at the distance in H between rational numbers and the singleton pi, oh, this would be a problem. This is not bounded. Maybe this is not a good example, but if I look at the distance between rational numbers intersection, say 0, 1, and 0, 1 minus the rational numbers. So I'm looking at the distance between rational numbers in 0, 1 and irrational numbers in 0, 1. Given any rational number, it's arbitrarily close to irrational numbers. So the first quantity is 0, as we saw, and so is the second quantity. Okay, so this is 0. So we can have two sets which are different from each other, but the distance between them is 0. These are even disjoint from each other. And the problem, as you see, is that they are not closed. Also, of course, they have to be bounded sets. Otherwise, you cannot even define the Hausdorff distance, because this may not be a finite quantity. But that's all. Once you take closed and bounded sets, and later we'll see we can pass to closures of sets and do this usefully for all bounded sets. So theorem is that the function dh is a metric on the set of closed and bounded sets on X, or rather in X. Indeed, we'll start the next video with a proof of this.